Hello everyone, we're back to talk about lecture 20. So nonlinear systems of differential equations. So we already talked about differential equations, linear and nonlinear, and then systems of differential equations that are linear. So now we're going to talk a little bit about what we do when we have nonlinear systems. The notes are a little bit long, but a lot of this is just review of some theorems and extension of theorems that we had for nonlinear scalar systems to the vectorial case. So don't be intimidated by the first 3 pages. We're going to go through them real quick. So just recall these definitions. We had these for scalar systems. Now we'll have it for vectorial systems. So a first order system of differential equations can be written in this way. If it's autonomous, it doesn't depend explicitly on time. And if it's linear, it can be written as ay plus b. If it's not, then it's nonlinear. Whoops, so my notes have some typos, yours won't have that. I had to recompile the LaTeX. So if it can't be written like 3, then this is going to be a nonlinear system. So just y prime is f of y in general. So let's say that we have an autonomous system. We also have this concept of an equilibrium solution for now a system of equations, which solves the fact that the y of e is a constant, otherwise known as, this is where f of y equals 0, which is the concept down here. So if this is a constant, then f of y should be 0. Whoops, here's our other typo, 4. Okay, so that should all be very familiar. Here's some more definitions. So we have an equilibrium solution to this autonomous differential equation. We say that it is stable if for every epsilon there exists a delta, so that every solution that starts within delta of an equilibrium satisfies the fact that it never gets, for any t, more than epsilon away from the equilibrium. So exact same definition that we have for the scalar case, but now we have norms instead of absolute values, right? If it's not stable, it's called unstable. If it's stable, we have these 2 other concepts that we may be able to specialize it to. So if it's stable and the trajectory y of t approaches ye, the equilibrium, as t goes to infinity, then we say it's locally asymptotically stable. If that is true for initial conditions that start within delta of the equilibrium, if we get this asymptotic nature for any solution that starts anywhere in the space where these guys live, then it's globally asymptotically stable. So we talked about this in lecture 17, where we had this theorem. We said if we had a linear system that looked like ay plus b, and it had an equilibrium, we would find the equilibrium here, right? Solving the right-hand side is equal to 0. And then the nature, the stability properties of that equilibrium just depended on A and the eigenstructure of A. If all of the eigenvalues of A had negative real part, then any solution of this guy would approach the equilibrium in the limit. That's to say that the equilibrium would be globally asymptotically stable. There's not a concept of local and global for this linear case because we only have this unique equilibrium. If you're locally, you're also globally. If you have one eigenvalue, at least one, that has a positive real part, then for any epsilon greater than 0, you would have some solution that starts less than epsilon, but goes to infinity as t goes to infinity. Starts less than epsilon of the equilibrium. So this is unstable. So the condition that we need to check for this linear system of equations is to look at the eigenvalues of A, right? If they have a negative real part, then we are stable because the solution should look like an exponential, right? Where the eigenvalues and the exponents. So this would decay to 0 when we have some stable equilibrium, versus if you have at least one that's positive, then you blow up. Okay, a couple more definitions. So this is linear, right? For the lecture today, the title said nonlinear. So how do we get there? So let's say I have a nonlinear system, this guy, with an equilibrium YE. If I have Y near YE, I can do this first order Taylor series approximation, right? I can add and subtract the equilibrium here and then do a Taylor expansion around YE. So this is really f of YE, and then times, plus some concept of the derivative of this guy times y minus ye. So what's the concept of a derivative for a vectorial function? It's the Jacobian, right? Since we know that f of ye is 0, because we have an equilibrium, this simplifies to this equation here. This is a linear approximation. This is of the form y prime is equal to a, this is some a, and then whatever, y plus b, where b is a times the equilibrium. So exactly the form for the theorem that we just reviewed. So we call this a linearization or a linearized system. And, oh, one more typo. So if we know that J is invertible, if it's not invertible, then this doesn't necessarily work, but if it's invertible, then we have a unique equilibrium. This is what we get from the theory we already built for linear systems. Okay, now theorem 2 for today, linearizing in the vectorial case. If I have an autonomous nonlinear system like this with a solution YE, an equilibrium solution YE, and F differentiable, so I can find the Jacobian, the linearized system looks like this. So if we have a globally asymptotically stable equilibrium of the linearized system here, then that same equilibrium is going to be locally asymptotically stable for the nonlinear system. We can't talk about global because this nonlinear system could have other equilibria, right? Like there could be other things going on. And this is only linearizing, it just gives you a local approximation of what's happening. But if I linearize and then use that theorem that we just had that says look at the negative, look to the real parts of the eigenvalues of A and make sure they're negative. If that's true, then I have globally asymptotically stable in the linearized system. And that implies that that same equilibrium is locally asymptotically stable for the nonlinear. And then if it's unstable in the linear system, it's also unstable in the linearized. So all of that should look familiar. Very similar to the vectorial, the linear but vectorial cases. So systems of linear equations that we've done before, as far as you know, the theorem that tells us we have to look at the eigenvalues of A to understand stability equilibria, and it should be just a vectorial extension of the scalar results for nonlinear systems that we've seen before. So yeah, hopefully none of that is like completely new. And let's go through 2 examples, one small and one big, so we can start to understand how to use these concepts. So this is just a kind of we're turning the crank example, and then we'll have a longer example where we look at an epidemic model. Okay, so just consider this nonlinear system. Y prime is f of y here. So I'd like you to determine all the equilibrium solutions, and then for each one, linearize near it and use the linearization theorem that we just saw to talk about its stability. Okay, so find equilibria. So let's say we need y1 minus 2 times y2 minus 3 to equal 0. So that means we have 2 cases. y1 is equal to 2 and y2 is equal to 3, right? So let y1 equal 2. The first one obviously was the first equation. Let's look at the second equation. That means the second equation becomes 2 plus 2 y2 times y2 minus 1 equals to 0. So what does that mean? That means y2 can be 1 or it can be negative 1, right? So I get I get 2 equilibria, right? I get, I guess we'll write them like this. Both of them have y1 equal to 2. And you have the second element as plus or minus 1. Now let's try the other case. If we have y2 is equal to 3, the second equation becomes y1 minus 6. And then y2 is 3, so this is times 2 is equal to 0. So y1 is equal to 6, and so the other equilibrium is 6 and 3. So 3 equilibria for this system. Great. All right. Is that? Oh no. Sorry, this should be plus, right? 3, so plus here. Yep. So minus 6, minus 6. Okay. Now we have 3 equilibria for the system. Okay, so let's find the Jacobian, plug in each equilibrium, and look at the eigenvalues. So what's the Jacobian? The derivative of the first equation, oops, you can't see it now. Move it down. Okay, with respect to y1 is 1, with respect to y2 is 1. Second equation, oh wait, no, excuse me. y2 minus 3 is a constant with respect to y1, y2 minus 3. And when I have the derivative with respect to y2, it's y1 minus 2. There we go, that's how we do derivatives. Second equation with respect to y1 will be y2 minus 1. With respect to y2, we can do like a product rule. So the derivative of the first guy with respect to y2 is 2 times the second, y2 minus 1. The derivative of the second guy is 1 times this, plus y1 plus 2y2. Isn't that right? Like 4y2 plus y1 minus 2. Yeah, that looks fine. Okay. In fact, I can like write this out a little simpler if we want. I said 4y2 plus y1 minus 2. Okay, that looks good. So for each equilibrium, let's write the linear system and see what we get. So when ye is equal to 2, 1, the linearized system, we'll write this, yl prime is going to be A. So that's the Jacobian. So 2, 1. So it's minus 2, 0, 0, 4 plus 2 minus 2, 4 times should be YL, the linearized guy, minus the equilibrium. This, right? Okay. So in this case, the eigenvalues just diagonal, so they're minus 2 and 4. 4 greater than 0 implies that YE is unstable. We'll be specific. Equilibrium of Y prime is F of Y. Because it's unstable for the linearized system, so it's unstable for the nonlinear system. Equilibrium number 2. So now we have 2, negative 1. So YL prime is, let's look to the Jacobian, Y2, so this is minus 4, 0, minus 2, so minus 4 plus 2 minus 2 minus 4 here, right? So the eigenvalues again are the diagonal. It's a triangular matrix. Oops, the equation is YL minus 2 minus 1. So the eigenvalues are minus 4 and minus 4. Okay, so they're both less than 0, which implies that YE, well, so it's going to be locally asymptotically stable is the most we can say. It's globally asymptotically stable for the linearized system, but it's locally asymptotically stable equilibrium of Y, sorry, not linearized. Y prime is f of Y, the nonlinear system. Excellent. Okay. Third, we have minus 6 and 3. So the linearized system is the Jacobian. Minus 6 minus 3 is minus 9. Oh, whoops, y2. Excuse me. It's a 0. Y2 minus 3. Y1 minus 2 is minus 8. Y2 minus 1 is 2. And 4y2, so 12, minus 6 is 6. Minus 2 is 4. YL minus 6 and 3. Does that look right? Looks okay. Okay, so what are the eigenvalues of this matrix? I'll subtract lambda. So I'll say minus lambda here times 4 minus lambda minus minus, so plus 16. So that's minus 4 lambda plus lambda squared plus 16 Is that a factor? I don't think so. Lambda is negative b plus or minus the square root of b squared minus, oh yeah, 4 times a times c. Okay, so it's some number. This is less than 0. So this is going to give me something imaginary. But the real part of lambda is 2, which is greater than 0, which implies that YE is what? Real part's greater than 0, so it's unstable. An unstable equilibrium of the nonlinear system. Y prime is f of y. Okay, so that's how we use it. I'm going to stop this video in the interest of file size, and then we'll restart, and we're going to build a mathematical model of an epidemic, and then we will use these same concepts to understand stability of its equilibria.